Good morning, mathematicians. I didn't realize it started streaming. Uh, how's it going? Start of a new week. Start of new cycle of proofs. You guys should be spamming chat more with things that you've been proving, especially on Mondays. Mondays are spam chat with things you proved day. Mind you, it's the first couple seconds, no one's here. I should probably say that again later, halfway through the video. Hello, Timothy. Good morning. Welcome to the office hour. Let's take a look. Where to start? I'll probably rant more about heck algebras today. Before there's while I'm waiting for viewer questions to come in. Well, let's do our usual by browsing Reddit to begin. What moment during or before a master's thesis in math one should ask the question of applying for a Ph.D.? Well, it depends. Who are you asking yourself the question? You should be asking yourself that question every morning when you wake up and look in the mirror. During this process do you decide you must look for a PhD or start looking for jobs in industry? Well, no, I don't think it's ever too early. I mean, especially your master's goes by quick, right? Because good morning, Jens. It's like if you're doing a 2-year master's, let's say, then already in fall of your second year, so you've only been there a year, already in fall of your second year, you're applying to PhDs, right? So it definitely goes by quick. And I mean, yeah, maybe first meeting is a little early, but yeah, I mean, if there's any doubt in your mind about whether you should go to a PhD or industry, then yeah, maybe give it more time to see. Although the weird thing is like, yeah, okay, people say you should do a master's to see if you want to do a PhD. I mean, the weird thing is, I think in a typical master's, your first year is normally coursework, and then the second year is research. But then the second year is like, well, you would have already applied to PhDs. I mean, I was fortunate in the way it worked out for me is I basically ended up doing summer research with my master's supervisor the summer before I started my PhD, and then that just bled into the rest of my research. So I had a taste of the research before the courses. Am I familiar with Olson's book on stacks? In the introduction, he says the prerequisites are familiarity with algebraic geometry and lists Hartshorne as an example. I don't know if I'm familiar with his book. Olson? Maybe I should look at that because I've been trying to get a better handle on stacks. Algebraic spaces and stacks. Is this the one? Wonder if I should get a copy. Introduction to the Theory of Algebraic Spaces and Stacks, intended for graduate students. However, skimming through the table of contents, this seems to not quite be enough. E.g., I don't think Hartshorne ever mentions étal. He definitely mentions étal. 100% he talks about étal morphisms. Does he talk about FPPF or FPQC? That I don't know. Do I have Hartshorne? I know I have Hartshorne, but is it just titled Hartshorne? Do I have to go digging? I don't think I've got a digital copy. I've got a hard copy somewhere in here, but yeah, I'm confident that Hartshorne does étal. Yeah, I mean, if you're, yeah, you could probably, I mean, okay, I'm not an expert on stacks, so take, I say this a lot on these live streams, take what I'm about to say with a huge dose of salt, but I think you could get pretty far without even knowing a tile you should probably know and have that as a concrete example, but I'm pretty sure you could just get away with like if you're doing more general stack stuff and not focusing on the like FPPF site in particular, you could probably get away without really knowing much about it and just go, oh yeah, that's a special class of morphisms, and so, um, I get a growth and deque topology. But I mean, examples of FPPF morphisms. I mean, I'm sure if you Google. Actually, someone sent me a really cool link. I don't want to. I don't want to go digging through their messages now in Discord, because I don't know if I want to reveal all that on stream. Actually, I don't think it's their actual name. I don't think it's their actual name. So how do I? Let me. If I do go to messages, how do I not reveal all my messages to you? Well, I pull this up on stream. I guess I can't. But anyways, it's a website where you basically tick a bunch of boxes for properties that you want your morphism to have in algebraic geometry world, and then it gives you a list. It'll spit out examples of morphisms with that property and without that property, but I mean, yeah, I don't think there's really that much. Like, I don't think it's a big deal. If that's the only thing that you're missing and you're concerned about is ATAL, FPPF, and FPQC, then my guess is that like I don't think it would be very hard to get yourself caught up on those things. I actually don't know it. I've never really worked a lot with FPPF or FPQC sheaves myself. Somewhat with ATAL, but that's actually something that actually I need to do some more basic, just it's one of those things where I feel like if I just do a handful of some rudimentary exercises on it, I'll just feel a little more comfortable. Yeah, probably the main thing, I guess. I don't think I've actually gone through it in detail before, but just checking that the fields Galois extensions give you ATAL maps between the schemes, and then that leads you. That's part of the computation of the ATAL fundamental group being the Galois group. I think that's a pretty simple exercise. I've just never actually walked through it in detail, so I feel like that's something I should go do because it's really not that bad, and then I'll be happier. Or have I done it? I don't know, but I still somehow I need to review it. Somehow there's some lack of comfort there. What else we got going on? What is going on in math world? Studies the regularity of functions. Yeah, harmonic analysis. Technically, my preprint has something about the regularity of an L function. I don't actually deal with that to any extent, but it does. It does have then. Oh, today's a good day because hello Fimnal. A new episode of Your Proofs Are Trash is dropping at noon, and also I should finally finish all the grading I have today, which means I will be free to return to beefing up some of the statements from my preprint before we send it off to a journal. So I'm excited to get back to work on that. Um, yeah, and then I'll be free to work on other things as well. So I'm looking forward to all these things. It's going to be a good day. And there's a talk. We have a little. My research group has a little mini seminar, and there's going to be a talk today. So good day for math. What else? What else? What else is going on? I don't know. Yeah, I guess that's about it for the Reddit news. Let's start yapping about math. Unless someone's got some more questions to stop me with. We could go over atalmorphisms together right now, actually. We could do that. Why not? Let's look up examples of atalmorphisms. Why not? Or we could probably even we could actually this is fun. I mean this involves some reading and working out of stuff. So maybe I should, read up on this before tomorrow or something. Because I don't want to spend just like 5 minutes of dead air of me staring at the screen. That's probably less entertaining. Okay, we'll talk about those soon, I hope, I think. But I'm going to jump back in time to a previous episode. So maybe I'll give you just a high-level summary. I'm interested in representations of a p-adic group. And we talked about a while ago that every representation, as opposed to, oh, good morning, Nicole. I don't think I've seen you in office hours for a while, so good to see you. We talked about how, in for finite groups, we can go for rep G to its ring of to modules over its ring of functions. We don't quite get. I mean, if we just repeat that story here, we don't get something quite as nice. But rather, it turns out that at least we can break up rep G into some infinite direct sum of categories, and for each of these individual categories, we can make it equivalent to HGK for some. So this is some ring of biinvariant functions. That Jordan algebra's problem set. Okay. Well, I hope you've made progress with it. You never learned ATAL, FPPF, FPQC stuff. I wish I'd learned more in uni. Yeah, fair. It is an interesting lack of stuff. Well, maybe you'll get to learn more of that stuff on this channel. Because, I mean, I've got my What the Sheaf series. I'm trying to keep it going and revive it. At the moment, I think, hopefully I'll have a new episode out on Wednesday. We'll see. But then the goal is to talk about quasi-coherent sheaves a bit. And then maybe affine schemes. And then I was thinking of going and talking about sheaves in general and talking about topos theory. But maybe I could make actually, I mean, if I'm going to talk about topos theory, it'd be a good excuse to take a detour into at least ATAL, if not FPPF and FPQC as well. So could happen. Good morning, Julie. Good morning. I can always make some one-off videos on occasion, too. I should do that more when I read up on some topic on my own and I just learn a little nugget of fact. I should be uploading little mini videos about that stuff. It'd probably, yeah. And the But in this whole story, we had somehow landed on the existence of a very special compact open subgroup called the Iwahori subgroup, and the idea was that so this is sort of smooth, which means locally constant. Oh, what am I doing? Turns out that this is smooth. Yeah, topoi, toposes, topiece. Take your pick. But this was going to be well, right now, Julie, we're talking about I'm talking about the Iwahori Hecke algebra. So it's just some sort of complex algebra that the Spark Notes. I talked about it in previous live streams a bit, but the Spark Notes are that it's some algebra that I can talk about representations of a p-adic group that I care about by talking about representations or modules over this algebra. And it classifies it captures an important class of representations of p-adic groups. And so, but we kind of gave it an abstract description. I'm not going to explain why these generators and relations exist. I mean, for that we need to dive into a little bit more about the specific structure of p-adic groups, but I am going to dive into some of the generators and relations. Does everything we learn in standard Galois theory course also apply to p-adic fields? Sort of, but actually there's an interesting the Galois theory changes a little bit. I mean, yes. So okay. Short answer is yes. Sorry. Yeah. Short answer is yes. Well, I don't know how you did your Galois theory course, but actually, so I taught a Galois theory course back fall 23, and there, I mean, we specialized to certain cases. Usually extensions of Q and finite fields are a main thing of focus, but a lot of the theorems, at least how I stated it in my course, applied to general field extensions to arbitrary field extensions when possible. I tried to state things quite generally. So yes, it applies to p-adic fields. Yeah, I think there are classical results particular to the rationals. Yes, certainly there are. And one thing, well, actually, I guess what I'm about to say, it is technically Galois theory, but this is maybe beyond what you learn in your Galois theory course. Once you get into algebraic number theory, you talk about not just so for the rational numbers, say, and some extension. You also talk about these things called rings of integers, which are like extensions of the integers, and you talk about prime ideals that in these rings that sit above some prime in the integers, and there's a whole fascinating number theory world and an interesting way in which these Galois groups interact with these primes. And this story sort of thematically, but not literally, gets repeated for the p-adic integers. But now, I don't know if you've ever heard the term places, but But basically, it's the idea that now you consider, so not only like if you have these rings of integers, so you have, of course, prime ideals that you consider in this ring of integers, but you also have embeddings. Say in the extensions of Q world, you have different embeddings into the complex numbers, and somehow like both of these are now put on equal footing through the theory of valuations. And this then you basically, over in P-adic land, you now get like a Galois theory of valuations, which I don't understand super well, to be honest. But I've read up a little bit, and it's really cool. The only thing that can really break is separability, which like doesn't really come up in classical Galois theory, as Q is of characteristic 0. Yeah. Well, Q, the P-adics are characteristic 0 as well. You studied like that as well, but don't really understand P-adic fields. Yeah, they're characteristic 0. Sorry, my throat's all weird today. I did a very, very hard run yesterday, and I've been like coughing weirdly since it. Finite fields are particular to, Z mod PZ, and thereby ruling out P-adics. Yeah. The valuation is well the right. So for Q, its ring of integers is just the integers, and you get you get a P-adic valuation for each prime. So that just says it just takes like a rational number, and it spits out how many times it goes P to the power of minus R, where the R is, you take M and P, you factor them so that M prime and N prime are both relatively prime, and you have P to the positive R out here. So this could be any integer, positive or negative. And so, overall, if P like divides this expression many times, then this will be really small, and vice versa. And this gives you sorry, the valuation should be R. The valuation is R, and then you define the absolute value to be P to the minus of the valuation. And so you get an absolute value for each one of those, and then you also get an absolute value for each embedding from the rational numbers into the complex numbers, but there's only one. So sometimes we write this with an infinity. That's just the Euclidean absolute value. Side question: how did I decide I liked arithmetic geometry? Since you didn't do pure math, you find it very overwhelming. Yeah, I guess I was always just attracted to things that were very overwhelming. I don't know. I mean, some people it's like, I mean, sometimes I'm like, damn, I should have picked more basic math, because hard math is very hard. But yeah, I don't know. There's a certain part of me and other people, I suppose, that are very attracted to something that seems like impossible to understand. When talking about this, am I familiar with the algebraic number theory book by Castles and Froelich? Of course, certainly. In fact, do I have Castles Froelich? No, I've got Froelich. I don't think I have Castles Froelich on my shelf. But yeah, certainly. So if you get the P-adic norm, then the P-adic fields are isomorphic to some extensions of Q. No, absolutely not. I mean, the P-adic norms. So what is the P-adic field? I mean, the definitions of the intrinsic of the p-adic numbers are intrinsic to that's right, Deepak, that's right. So the p-adic numbers, so just like how do we build the real numbers? What's one way to build the real numbers? Well, we take the p-adic numbers and we take the ordinary like absolute value, and then we look at Cauchy sequences, and we perform the Cauchy sequence completion. So for any metric space, you can create a metric space in which all Cauchy sequences in the original space converge. And so that's how we produce the real numbers. The p-adic numbers is just playing the exact same game, but we take the Cauchy sequence completion with respect to the p-adic norm. So yeah, so once you forget, I mean, you can do that and then forget you ever had a norm, but still the field you have is, oh, sorry, you know what? I mean, sorry, it is an extension of the rational numbers. Sorry, you're absolutely right. Sorry. I mean, the rational numbers, you do get a copy of the rational numbers sitting inside here, just as you do with the real numbers. But I guess we normally don't think about this fact, right? Like what is it's not a Galois extension. It's some weird transcendental extension, right? Like this is uncountable as well. Isn't QP the completion in respect to ultra norms? Yes. Yeah. That's that. Yeah, non-algebraic extension. Yeah, Q is the prime field, exactly. Yeah, so it's a weird yeah. But going back to this, yes, characteristic 0, yeah. And so going back to this idea of valuations, it turns out, so we have like p-adic absolute values, and so we have absolute values corresponding to each of the prime numbers, and then we have one absolute value corresponding to the unique embedding in the complex numbers. For a more general extension of the rational numbers, we play this game again. For every prime ideal in the ring of integers, we now get a p-adic metric, but where this is mathfrak p, and now we might have multiple different embeddings. We might have multiple different embeddings from the from your field E into the complex numbers. In general, the number of such embeddings is going to be R plus 2 times S. So these are the embeddings that land in the reals, and this is the embeddings that don't land in the reals, but they come in complex conjugate pairs. And then, so it'll turn out that the complex conjugate pairs give equivalent embeddings, but the idea is we get an absolute value now for each of these, where we first, it's defined by first simply applying our embedding and then just evaluating at the ordinary complex absolute value. And so these are, this is kind of why they're called like places, or some people say primes, to now extend beyond prime ideals and to also include embeddings, and then these are sometimes called primes at infinity. Yeah. As we're going into this direction anyways, can we maybe talk about the Adeles ring later, please? Yeah, we could talk about it now. So, yeah, the idea is then, how do we form the Adeles? Well, the sort of idea is, well, first let me say Ostrowski's theorem, one of my favorite theorems in all of mathematics. Ostrowski's theorem says that up to homeomorphism, which is to say topological equivalence, and this is a generalization of Ostrowski I'm about to state. The norms on some finite extension, does it have to be Galois? Let's just say Galois to be safe. Some Galois extension, E over Q, are given by, I mean, I guess is basically what I just said. So everything I just said, oh, all of these things do give us a norm, but in fact, all of the norms are either a p-adic norm for some prime ideal in the ring of integers, or it's given by some embedding, where of course the complex conjugate embeddings are equivalent. And so one might then say, well, okay, so I have all of these, and I can take so then we get the p-adic integers for each of these primes, or the E sub sigma adic integers for all of these embeddings, which is just, again, this game of Cauchy sequence completions. So I have all of these, and these are the only ones I have. So instead of going one by one and studying them, why don't I just multiply them all together and study them in one shot? So for example, we might try to take, the real numbers times the 2 adics times the 3 adics times the 5 adics, and so on and so forth, and just say, okay, yeah, let's go to town and just study this giant thing all at once. Why not? The problem with this is the nice thing about all of these fields is that they're locally compact. They're locally compact. And what that means is we can basically do analysis on these fields, right? They've got these. So not only is it the case that these fields have metrics and analytic properties, but that means that each of these fields, by the way, sometimes we call R Q sub infinity. So when we say prime less than or equal to infinity, we mean either a prime or infinity. When we're looking at these fields, this means that QP, the underlying abelian group, and the group of non-zero, the multiplicative group of non-zero elements, these are locally compact topological groups, and thus they all have. I always spell har wrong. No, it's 2 A's. Yeah, they all have Gödel given measures on them. So this just screams, okay, we want to be able to do, now we can have a whole theory of integration on these things, which is useful to have. But then the problem is if we multiply, if we just take this infinite product of all of these fields, now we lose local compactness. We may not retain local compactness. So what we do is we say, okay, well, I'm not going to quite take the full product. I'm going to take, so just for this, just for the finite primes, I'm going to take this thing called the restricted product, where what does that mean? It means almost all, meaning all but finitely many, almost all coordinates of this. So this is we can view it as some infinite vector. Almost all of these, by the way, I'm yapping about this. I'm sure I've yapped about this exact same thing in previous streams. Also, I do have videos, some of my videos that are Introduction to Langlands or whatever, talk about all the same thing. Possibly slower, possibly in more detail. So this says only finitely many of these. So maybe it's just A3 Maybe it's just the A3 coordinate, or sorry, and this one. Sorry, I didn't say what it is. Almost all coordinates have to lie in the p-adic integers, which is an open compact subgroup. So it could just be, say, the 2 coordinate and the 5 coordinate, and then everything else lies in the ZP. And because these are open compact subgroups, this restricted product is still going to be locally compact. And so we define the Adeles. Well, I as an example, I gave the p-adic, but we can form the Adeles for any number field. And that's just going to be, well, first we'll have this product over, this finite product over these things, over the embeddings, and then we'll have a product over our prime ideals of the other completions, but it's the restricted direct product. Same idea. And that's the Adeles. And so we can do calculus or integration theory, at least, on the Adeles by defining them in this way. And in particular, we can set up stuff so like we can basically, so part of what led Tate to write things in terms of the Adeles in his famous thesis is that now we can write things like zeta functions and L functions can now be written in terms of integrals over the Adeles. And we can prove things like functional equations, like, for example, the functional equation of the Riemann zeta function, which, you know, relates like zeta s. We have some sort of other terms to like zeta 1 minus s. But now we can sort of do this with whole families of zeta functions in all directions, all at once. And we kind of have some nice tricks to help us do this, like using things from like the theory of like integration and like, I don't know, if you've seen certain proofs of like the analytic continuation of the Riemann zeta function, you use like Poisson summation, and this, like, you can take these ideas, these sort of ideas, and extend them to much more general scenarios. And so in particular, by extending these to like arbitrary number fields, we can prove theorems about zeta functions much more generally. Why don't we need the restricted product on the embedding ones? Well, because really the embeddings, there's only finitely many terms here, right? And so, I mean, we're basically using Tikhonov's theorem, which says that a product, even an infinite product of compact spaces, is compact. Yes, because they're finitely many, exactly. So we're using the fact that a product of compact spaces is compact. So let's say we have just the embeddings, and okay, I'm accounting for the complex conjugate pairs of, you know, pick a unique one for these, call it sigma 1 up to sigma n. So if you want to prove that part of it is locally compact, what's the open set you're going to take there? Well, I mean, so you take like x1 to xn, you know, living in this product, and right, I know I said this wrong on stream the other day. So locally compact, actually this means every point should have an open neighborhood, and that open neighborhood is a subset of a compact space, I believe. And so how are we going to build up our locally compact subset here? Well, I mean, each I we know we can choose an open neighborhood around each I. and a compact set containing that neighborhood. So of course this entire vector is just going to be in this open neighborhood contained in this product of compact sets. So this will be compact, and okay, so we've proved that for finitely many things it's locally compact. But the reason that we're taking the restricted direct product now, like let's think about the case, let's just think about the p-adic numbers. Like we're taking this restricted direct product, and how are we able to choose local compactness? Well, we know, right? We know that if it's locally compact, so say we've got this x equal to x2, x3, ... let S be the subset of primes where x sub p is in S if and only if xp is not in zp, right? S is finite, right? S is finite. So now choose for each p in S. We know that we can choose an open neighborhood. We know that we can choose an open neighborhood UP contained in KP and a compact set containing that neighborhood, right? So then basically we're going to take like a product of sets, although I need to be careful because the product topology and the box topology are not the same thing once we go to the infinite place. So I might write something that's quasi wrong in a moment. But the idea is this: we're going to take as our open set, we're going to take the product over all UP, so over all primes, but where so UP is defined to be it'll be, wow, gosh, this is bad notation. Okay, let me call it VP. Let me call it VP, where VP is defined to be one of these UP when P is in S, and then it's just in ZP otherwise. And so by construction, oh gosh, what am I saying? This should be KP. This should be KP. We're trying to create a compact thing here. Call this K. I don't know. VPK. Yeah. So by construction, X is gonna be in K. Okay, and there's an open neighborhood we can sandwich in between these things as well. So I don't know. Maybe that explanation was a little rushed. But I hope it's somewhat comprehensible. Yeah. One of the other nice things too is we also have this formula. If you take the product of a rational number over all the p-adic norms, it equals 1. Which is it's a very simple proof. It's a very straightforward proof. You literally just unpack the definitions. But somehow, I don't know, I just find this fact so beautiful. It just really speaks to the completeness of all of these things. I don't know. Yeah. Yeah, like I think maybe there's one thing. One of my in last semester, one of my students I was mentoring for my local mentorship program. I think we proved, what is it? I think the result is, so the p-adic absolute value actually determines a complex character. And actually, I've talked about this. In fact, for all complex numbers S, you get a character, which, by the way, is smooth, which is to say it's locally constant. And in fact, we've already encountered this idea when I was talking about representations of p-adic groups and building up the theory of multi-segments and stuff over the bunch of the streams in the last couple of weeks. And it turns out that if you integrate over, I believe it's the multiplicative group, and you integrate this character over the multiplicative group. Wait, am I about to say something wrong? Because normally when we integrate characters, they're either 1 or 0, but that depends on our normalization. At the risk of saying something wrong, actually, for what I'm about to say, it might actually be the additive character. It might actually be the additive character that we integrate with respect to the Haar measure. But then we use this integral pops up. Yeah. Because the result somehow there's a way that you relate the additive and multiplicative Haar measures, and that's it's a combination of this and the normalization of the Haar measure that we choose to pop out. Excuse me. Which gives us this term. And that might look familiar to you from the product expansion of the Riemann zeta function. And that's no coincidence. So this is basically what I was talking about before, about how we relate like the Riemann zeta function. So if we took some sort of I should have put in a P there. So somehow we can combine these all together into like one big function, and then integrate that function over the Adeles, and there's a result that tells you that it basically, the finite Adeles, by which I mean just the product over the primes, restricted product over the primes. So that just becomes the product of all of these local integrals, we might call them, and then by what I just said, that becomes this term, which of course is just the Riemann zeta function before we've analytically continued it, evaluated at the complex number S. So, yeah, so that's cool. I think that's cool. But then also, so notice that this integral was just performed over the finite Adeles. So including the real numbers as a term can sort of be viewed as giving you, like, when we have this, I'm going to use uncommon notation here. This is not normally what lambda is used to denote, but so we can basically view as, now if we include a term by also integrating over the real numbers, we can view this as giving us some sort of normalization factor, lambda s, which comes out in front here, right? So we see that each of the p-adic numbers contributes one of the terms in this product. But then to get the analytic continuation, somehow the real numbers, in a sense, can be viewed as responsible for this. So maybe I'll pull up the Riemann zeta function. Let's find its analytic formula. Yeah, so here's the term, right? And so here we see, like, this sort of ordinary part of the Riemann zeta function is just coming from the p-adic numbers, and then somehow, like, we can view this as some sort of, like, this transcendental function, the presence of the gamma function. Somehow this is like the contribution from the real numbers when you're taking an integral over the Adeles. Hopefully that was moderately comprehensible to some people. But yeah. There's so many wonderful things that would be great to talk about on this channel with actual, go slower and do a series on. But, there's not enough hours in the day ever. But it would be fun to do this in more detail. Yeah. Well, there's no more questions about that. Maybe I'll go back to yapping about this affine Heck algebra. And right now, we just know it as some abstract algebra of functions. Right? This is just some abstract algebra of functions. But I can give a very particular description of it. So we'll have to talk about two important things to do with algebraic groups. So first, there's something called the Weyl group. There's many ways to define and talk about this, but one way is to take the the normalizer of a torus, a maximal torus, and mod out by the torus. So this is the Weyl group. It turns out it has a pretty simple description in many cases. In particular, for GLN, it ends up being just isomorphic to the symmetric group on n elements. So remember that our torus in GLN is just the invertible diagonal matrices. And it turns out that once you compute the normalizer, you find that each equivalence class has a representative given by a permutation matrix. So, for example, in GL3, like, remember the permutation matrices are just literally you take your n by n matrix, and then you swap, say, just the rows according to some permutation in Sn, right? So let's say we have this, and we could look at the matrix corresponding to the 2-3 permutation, and that will be this matrix, for example. You've heard this is a complicated topic. It takes a while to get the hang of it. Yes, indeed, William. Yes, indeed. Sup, chat, and K-theory. Hello, you're taking your first abstract algebra course. Any general tips? You like topology. So if it's your first course, I'm guessing that means like groups and ring theory. I love Aloufy. I never shut up about Aloufy. I recommend reading Aloufy. General tips. As a general tip, I mean, this is something that's so general it applies to every math course. Is always have on hand. So first off, and I've even used this technique into grad school. I know that the sexy part of math is not the memorization, but you do need to memorize things. So throughout my mathematics education, I have used flashcards to memorize all the important definitions, because if you don't, this is the number one important thing. If you don't know, if a question asks you to prove that something is a normal subgroup and you don't know what a normal subgroup is, you're absolutely screwed. So even if you forget every theorem you ever learned in class, at least in theory, if you remember your definition, you could possibly maybe still prove something about that definition on a midterm or final. So using flashcards to remember definitions, theorems, of course, statements of the most important theorems, and of course proofs. So I would literally do this. I would when I was, instead of pulling up my phone when I was waiting for the bus or whatever, when I was or in line at the grocery store, I would pull out my flashcards and I would literally go through them, and I would look at the statement of a theorem and I would try to prove it in my head. And look, I'm not a super genius, right? I couldn't do it at first. I would get maybe a line in. I would go, let X be in G. Then, and then I would look at it. I would read the proof, and then I'd put it to the back of the pile. And I'd go for the next one. And at first, of course, I couldn't do anything. But then normally by the time I got to the exam, I could look at the flashcard, read the statement of the theorem, and then prove the result in my head. Just go through the steps in my head. And I'm not a super genius. I just kept practicing a lot. Also, simply the act of writing these things out helps. Now, I'm a big tech person. Throughout my undergrad, master's, and PhD, I will live tech notes in courses and sometimes even in talks and seminars, unless they go too fast. But nonetheless, it is true that studies have suggested that the process of physically writing something down is actually a more effective way to commit something to memory. And so I believe not only, of course, having the flashcards to consult regularly is very important, but also just the physical act of writing things down is shown to be helpful for you to retain your memory. So definitely flashcards. The other thing that you want to memorize, to have on hand, is examples. And this goes for any course, right? Examples and non-examples. So every time you encounter a concept in this course, make sure you have an example and a non-example of that concept, and that you're able to prove that those are examples or non-examples. So even for a group, have an example. The integers under addition. Non-example. The natural numbers under addition. Normal subgroups. Have again, examples and non-examples. So normal subgroups. AN as a normal subgroup of SN. AN is a normal subgroup of SN. A non-example. Gosh, I can't think of a non-example. I don't know. What the diagonal matrices in GLN, is that even true? Yeah, that's true. That's true. But just time and time, right? Have an example. If you come up with a principal ideal domain and a non-principal ideal domain. Never used flashcards before, but might implement it. Cool. Main text is Lang. I've never actually read Lang. You're thinking of using Aloofy as a complement. Great idea. Aloofy is great for self-study. Yes, I mean Chapter 0 Aloofy. Or Notes from the Undergrad. Well, actually, Notes from the Undergrad is brand new. I haven't seen it yet, but actually a professor here at my university, she was at AMS, and I think she flipped through a copy that was there, and she was like, "Oh, this looks really good." When she came back, she was like, "Hey, Kristaps, you should check out this new," because she knows that I love Aloofy and that I taught one of our algebra courses using it. So she was like, "Kristaps, you should check out this new book from Aloofy." So. Yeah, I do mean Chapter 0, but hey, look at Notes from the Undergrad. That's probably good as well. I trust that man wholeheartedly. So I think that's where we're gonna leave it. I think that's where we're gonna leave it for today. I still have more coffee left because my Got it in my thermos, but Notes from the Underground is weird for first algebra because it starts with rings. Interesting. Interesting. Yeah, well. Yeah. That's very interesting. Yeah, that is strange, but I don't know. Maybe I've got to take a look because I trust a Luffy. I trust a Luffy. So, anyways, time for me to go prove some theorems. Time for you to go prove some theorems.